Hi students, Professor Nugent here. In this video, we're going to discuss what assumptions we need in place in order to be able to make causal inference using multiple regression. We will conclude with what our sampling distribution is. In the last video, we discussed the measures of fit for multiple regression model. We looked at root mean squared error, the standard error of the regression, both measures of the standard deviation of the OLS residual, where the standard error of the regression has a degrees of freedom correction. We also looked at the coefficient of determination R squared and adjusted R squared, where adjusted R squared now has a degrees of freedom correction. Okay, now back to what we're discussing in this video: least squares assumptions for causal inference in multiple regression. If we let beta 1, beta 2 through beta k be the causal effects in our multiple regression model, then we can write our multiple regression model as this equation. Let's write this equation as equation 3. yi is equal to beta naught plus beta 1 times x1i plus beta 2 times x2i plus all the way through to beta k times xki plus ui for I equals 1 through n. Our assumptions are the following. Number 1, the conditional distribution of u given the x's has a mean of 0, that is, the expected value of u, given that x1i is equal to x1, all the way to xki is equal to xk, it's equal to 0. This is the same as with the univariate case, only now we have more x's to worry about. 2. x1i through xki and yi for I equals 1 through n are iid. Again, same as univariate case, only we have more x's. 3. Large outliers are unlikely for all of our x's and for y. In other words, they have finite fourth moments. Finite fourth moments. Between 0 and infinity. Expected value of x to the power of 4, x1 to the power of 4 is between 0 and infinity. And so on and so forth through x to the k, and the same for y. Finite fourth moments for x1 through xk. So assumptions 1 through 3 are the same as the univariate case. Number 4 is new to the party. Number 4 states that there's no perfect multi-collinearity, which basically states that one regressor is not a perfect linear representation of another regressor. We will spend time thinking about that. Let's look at assumption 1 first. The conditional mean of u given the included x's, the included regressors, is 0. This has the same interpretation as in regression with a single regressor. Failure of this condition leads to omitted variable bias. Specifically, if an omitted variable 1 belongs in the equation, so it is in u, and 2 is correlated with an included x, then this condition fails and there's omitted variable bias. The best solution, if possible, is to include the omitted variable in the regression. If it is not possible to include the omitted variable in the regression, then a second related solution is to include a variable that controls for the omitted variable by proxy. So sometimes we think of well-being. If well-being were an omitted variable, how could you include a measure for well-being in the regression? That would be quite hard. It's hard to measure well-being. A way that economists often measure well-being across countries is by using income per capita, so that it would be a variable that would control for well-being. It is a proxy for well-being. All right. So assumption 2, that our x's and y are IID. This is satisfied automatically if the data are collected by simple random sampling. In assumption 3, large outliers are rare. We have finite fourth moments. This is the same assumption as we had before for a single regressor. As in the case of a single regressor, OLS can be sensitive to large outliers. So we need to check our data. You need to plot the data, look at the data, see that there are no values that are very large, that there are no typos or coding errors. And if there are, then we need to clean the data set to remove those observations. Alright, now let's talk about assumption number 4. There is no perfect multicollinearity. Perfect multicollinearity is when one of the regressors is an exact linear function of the other regressors. An easy example to think about is if we suppose that we accidentally include the student-to-teacher ratio variable in our regression twice, where the student-to-teacher ratio, this variable str, is an exact linear function of this one, right? Str equals 1 times str. So where this is x2, this is x1. So x2 is an exact linear function of x1, and so we have a problem. We cannot estimate the coefficient on x2, so it is dropped. Theta will just drop it. It's going to drop that variable like it's hot. Can't estimate that coefficient. Why can't we estimate that coefficient? Well, in that regression, beta 1 is the effect on test score of a change in the student-to-teacher ratio holding the student-to-teacher ratio constant. What? That's crazy, right? Okay, so this is x1, right? This is x2. So beta 1 represents the change in y given a change in x1 holding x2 constant. But x1 equals x2. So how can you change x1 holding x2 constant if x2 equals x1? You can't. So that's why theta drops it like it's hot. So we're going to return to perfect and imperfect multicollinearity shortly with more examples. But with these least squares assumptions in hand, we can now derive the sampling distribution of the betas in our multiple regression model. The sampling distribution of the OLS estimator under the 4 least squares assumptions. Our sampling distribution of beta 1 hat, it has a mean of beta 1 that holds for all of the OLS coefficients 1 through k. The variance of beta 1 hat 1 through k, it is inversely proportional to the sample size n. So as your sample size goes up, the variance of beta 1 goes down. Other than its mean and variance, the exact finite n distribution of beta 1 hat, it is complicated, but for large n, beta 1 hat is consistent, so beta 1 hat converges in probability to the population value of beta 1, and the standardized value of beta 1 hat minus the expected value of beta 1 hat over the square root of the variance of beta 1 hat, it is approximately distributed according to the standard normal distribution, thanks to the central limit theorem. These statements hold for beta 1 hat through beta k hat. So conceptually, there's nothing new here. These are all the same, only we have some new coefficients to work with. that is it for this video. In the next video, we will discuss multicollinearity, perfect and imperfect.